Hello and welcome back. In this video we will be covering threat modeling, an overview of threat modeling methods, threat scenarios, and then look at the methods we use in our TARA that also align with the ISO SC 21434 standards. In addition to that, we will review some helpful references. Threat modeling is essential for identifying potential threats and potential vulnerabilities and assessing their impact on systems. ISO SC 21434 emphasizes the need for a structured approach to threat identification, helping organizations prioritize risks and develop cybersecurity goals. The main objective is to systematically analyze assets, identify potential threats, and mitigate them before they can be exploited. This process is critical in ensuring the safety and reliability of modern vehicles, especially as they become increasingly connected. There are several methodologies to conduct threat analysis effectively, such as STRIDE, Evita, and TVRA, and PASTA. STRIDE. This framework focuses on categorizing threats into 6 types: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. It's a highly efficient model for analyzing known threats in well-defined systems. Evita and TVRA. Evita, which stands for E-Safety Vehicle Intrusion Protected Applications, was specifically tailored to the automotive sector, and TVRA, which stands for Threat, Vulnerability, and Risk Analysis, can be tailored to the automotive sector. PASTA, known as Process for Attack Simulation and Threat Analysis, a more process-driven approach that emphasizes threat analysis through the software development lifecycle. These are just a few frameworks that help us assess the feasibility and impact of potential attacks. The threat modeling process involves several key steps. Identifying assets. The first step is to identify crucial assets within the system, such as electronic control units, sensors, communication interfaces, software components, and data. These assets are what we aim to protect from potential threats. Create an architectural overview. Next, we develop a comprehensive overview of the system architecture, including data flows, control flows, and communication channels. This helps us understand how different components interact and where potential vulnerabilities might exist. Identify threats and vulnerabilities. Using methodologies like attack trees, STRIDE, and sometimes leveraging open source threat matrices, we systematically identify potential threats to the system. This step involves analyzing possible attack vectors and entry points that could be exploited by attackers. Analyze impact. Once threats are identified, we assess the severity and impact of each threat. This includes evaluating the consequences on safety, functionality, privacy, and compliance. The goal here is to prioritize threats based on their potential impact and the feasibility of exploitation, allowing us to focus on the most critical risks first. Let's dive into an overview of different threat modeling and risk assessment methodologies commonly used in automotive cybersecurity and other industries. Each framework has a specific focus and serves different purposes, depending on the nature of the threats and the type of systems being analyzed. Now, just as a note, there may be more methodologies that are not covered here, but we wanted to provide some reference to other methodologies other organizations use. STRIDE is a qualitative framework used on security threat identification. It categorizes threats into 6 types: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. The scoring method in STRIDE is qualitative, analyzing each element based on its threat type. The process involves 3 main steps: identifying the threat, classify the type of threat based on STRIDE categories, and mitigate it using appropriate security measures. Strengths of STRIDE include its simplicity and effectiveness in identifying common security threats. However, it lacks quantitative scoring and may not adequately address privacy-related issues, which can be a drawback in more complex systems. Moving on to PASTA, which once again stands for Process for Attack Simulation and Threat Analysis. This framework takes a risk-centric approach by focusing on both business and technical impacts. It uses quantitative risk scoring to assess the severity of identified threats. PASTA follows a detailed 7-step process. preparation, threat analysis, vulnerability analysis, attack modeling, risk analysis, impact analysis, and risk management. This comprehensive process makes PASTA ideal for scenarios where you need to understand the broader implications of threats on business objectives. However, its complexity requires a thorough understanding and can be challenging to implement. LIN-DUN is specifically designed for privacy threat identification. It focuses on threats related to linkability, identifiability, non-repudiation, detectability, disclosure of information, unawareness, and non-compliance. The scoring method here is qualitative, with a focus on analyzing privacy threats in systems. The steps include identifying privacy issues, analyze the impact, address the identified risks. LIN-DUN is highly effective in privacy-sensitive environments, but is limited to qualitative assessments and may not be as comprehensive for broader security issues. Next, we have DREAD, which is used for threat prioritization based on a weighted scoring system. DREAD evaluates threats based on damage potential, reproducibility, exploitability, affected users, and discoverability. Each threat is rated numerically, which helps in prioritizing threats based on their impact and ease of exploitation. However, one of the drawbacks of DREAD is that its subjective nature can lead to inconsistent scoring if not managed carefully. The next three are matrices and frameworks that can be used, such as MITRE, ATM, or CVSS. The MITRE framework focuses on adversary tactics, techniques, and procedures. It's widely used to simulate real-world adversary behavior, allowing organizations to understand how attackers might target their systems. This framework uses a qualitative scoring method to map tactics to techniques, which is helpful in developing defensive strategies. This framework is excellent for simulating adversary behavior and building robust defense strategies, but it requires detailed knowledge and can sometimes be overwhelming due to its comprehensive nature. CVSS, otherwise known as Common Vulnerability Scoring System, is a widely recognized framework for vulnerability assessment. It uses a numeric scoring system ranging from 0 to 10 to assess the severity of vulnerabilities. The score is determined based on factors such as the attack vector, complexity, required privileges, and potential impact. CVSS is effective for scanning vulnerabilities and penetration testing, but it focuses specifically on identifying vulnerabilities rather than providing a broader threat analysis. Lastly, the Automotive Threat Matrix, which is similar to the MITRE framework, is tailored specifically for the automotive sector. It focuses on identifying and mitigating threats unique to automotive systems, especially connected and autonomous vehicles. The framework uses both qualitative and quantitative scoring methods, similar to STRIDE but adapted to the automotive context. ATM covers a 7-step process similar to PASTA, which includes identifying threats, classifying them, mitigating risks through preparation, threat analysis, vulnerability analysis, attack modeling, risk analysis, and impact analysis. ATM's strength lies in its ability to address scenario-based learning and risk management specific to automotive cybersecurity, making it highly relevant for organizations that need to secure complex automotive systems. Now let's focus on understanding the vehicle attack surface. In the context of automotive cybersecurity, the attack surface refers to all the potential entry points that an attacker could exploit to gain unauthorized access to a vehicle's systems. By identifying these attack surfaces, we can better understand where vulnerabilities might exist and develop strategies to mitigate potential threats. First, we need to consider the engineering and supply base. This includes vehicle component software, for example, firmware in the ECUs that could be tampered with. Vehicle component hardware. Attackers may target physical hardware during the manufacturing process. Manufacturing. Supply chain attacks are a significant concern here. Malicious code could be introduced during component production or assembly, potentially compromising the vehicle before it even reaches the customer. Addressing risks at the engineering and supply chain level is critical, especially as vehicles become more reliant on complex, interconnected software systems. Next, local attack vectors. These include physical interfaces and networks within the vehicle, such as CAN bus, the controller area network, which connects various ECUs. Compromising the CAN bus can allow attackers to control vehicle functions like braking or steering. Automotive Ethernet, used for high-speed communication between systems, particularly in modern vehicles. LIN, Local Interconnect Network, and MOST, Media-Oriented Systems Transport. These are other in-vehicle networks that manage different subsystems. USB ports, often used for diagnostics, firmware updates, or media playbacks. USB ports can be exploited if attackers gain physical access to the vehicle. Protecting local interfaces involves implementing strong access controls and encryption to prevent unauthorized access. Another crucial area is remote attack vectors, which have become more prevalent in the rise of connected vehicles. Key entry points include connected vehicle server infrastructure. Attackers could exploit vulnerabilities in cloud servers used for telematics and vehicle management systems. Diagnostics and OTA updates. Remote software updates are convenient, but it can also be a potential vector for introducing malicious code if not properly secured. Securing remote entry points requires robust encryption, authentication, and intrusion detection systems to protect against unauthorized access. Lastly, we have proximity attack vectors, which involve wireless communications and devices that interact with the vehicle. These include radio frequency and GPS. Attackers could spoof GPS signals or interfere with radio communications. Bluetooth and Wi-Fi, often used for infotainment and driver convenience features. These wireless protocols can be entry points if not properly secured. Cellular networks and vehicle-to-everything. These are used for connected vehicle features like real-time traffic updates or autonomous driving support. However, they also increase the risk of remote attacks. Sensors and mobile apps. Hackers can manipulate sensors such as LiDAR or cameras or exploit vulnerabilities in companion mobile devices to gain access to vehicle systems. Implementing strong security protocols for wireless communication and proximity-based services is essential for reducing the attack surface. In summary, understanding the vehicle attack surface is crucial for developing a comprehensive cybersecurity strategy. We talked a bit about threat modeling methods earlier and only briefly mentioned STRIDE and attack trees. Let's dive into the concept of attack trees first. Attack trees provide a quantitative approach. The idea is to use a tree structure to graphically represent attack possibilities. At the root of the tree is the attacker's primary goal. This serves as our target. Each branch represents different pathways an attacker might take to achieve that goal. By visualizing these attack paths, we can better identify vulnerabilities and prioritize mitigation efforts. Each subsequent branch represents an attack vector or step that an attacker could take. To assess the risk associated with each path, we can use the Common Vulnerability Scoring System. CVSS helps us evaluate the severity of potential attacks and prioritize which ones need immediate mitigation based on factors like exploitability, impact, and complexity. An essential part of using attack trees is attack path validation. We start by identifying the various attack paths an adversary might use to reach their objective. For example, an attacker could compromise the navigation ECU via a cellular interface, transmit malicious control signals, and then spoof signals to the power switch actuator to turn off the headlamp unexpectedly. By mapping these paths, we can validate our security controls to ensure they effectively protect against these identified threats. As the saying goes, security is not a product, it's a process. Attack trees help us continuously refine that process. Now let's break down the structure of the attack tree using the example provided. The attack objective at the top of the tree is associated with the severity of the potential impact. In this case, the objective is to compromise the integrity and availability of the headlamp system. Below that, we have the attack path, which is associated with the feasibility of different methods attackers might use. Each branch shows the steps an attacker could take: compromising the navigation ECU from a cellular interface, transmitting malicious control signals, forwarding spoofed signals to the power switch actuator, ultimately sending malicious signals to turn the headlamp off unintentionally. It is important to note that there are also AND, OR gates that are involved in attack trees to indicate whether all conditions below the gate must be satisfied for the attack to succeed. The OR gate is when the attacker can take any of the several different paths to achieve the same objective. In this example, this would be an AND gate. By analyzing both the severity of the attack objective and the feasibility of the attack paths, we can better prioritize our cybersecurity efforts. As we mentioned earlier, attack tree methodologies generally use CVSS-based approach to break down feasibility determined based on exploitability metrics of the attack vectors. Here's a reference if you'd like to dive more into the latest CVSS version. The STRIDE methodology, which is a qualitative threat analysis method widely used in the industry for identifying cybersecurity threats. One of the key reasons why STRIDE is so effective is that it focuses on the purpose of the attack, rather than trying to account for every possible type of attack scenario. This approach helps streamline the threat assessment process, making it more targeted and efficient. Instead of overwhelming us with countless possibilities, STRIDE simplifies the analysis by categorizing threats into just 6 distinct types: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. I would like to mention that oftentimes we hear this phrase, "think like a hacker." However, thinking like an attacker doesn't give us any structure or any help on how we can threat model. There are many factors that come into play, and the phrase might be confusing. That is why we want to use useful techniques like STRIDE, which is why STRIDE is so commonly preferred over other methods. Let's break down a few key reasons. Repeatability. STRIDE provides a consistent and repeatable framework for assessing threats. This means that whether you're evaluating a new system or visiting an existing one, STRIDE offers a structured way to identify threats, leading to reliable results. Efficiency. It's particularly effective in known design contexts. When you're working with familiar system architectures, STRIDE helps quickly pinpoint relevant threats without getting bogged down in unnecessary details. Ease of documentation. Compared to more complex methods, STRIDE is easier to document. It's a straightforward process, which makes it simpler for teams to communicate findings and implement the necessary security measures. Direct control association. Finally, STRIDE facilitates a clear alignment between identified vulnerabilities and the controls needed to mitigate them. This direct association makes it easier to translate threat assessments into actionable security controls, ensuring that vulnerabilities are effectively addressed. Let's take a closer look at some concrete examples of how the STRIDE methodology applies to automotive cybersecurity. In this table, we've mapped the 6 types of threats defined by STRIDE to specific vehicle assets and highlighted the corresponding security properties, focused on CIA that may be compromised. Spoofing. Spoofing occurs when an attacker pretends to be something they are not. In the automotive context, this can involve vehicle sensors or ECUs. For instance, a malicious actor might inject false signals to a vehicle sensor, leading it to perceive incorrect data. This could compromise integrity, as the vehicle might make incorrect decisions based on falsified information. Tampering refers to an attacker altering data either while it's stored or as it's being transmitted. In vehicles, this can affect ECU software. An example would be altering firmware in an ECU to change its functionality, which could have serious safety implications. The primary concern here is also integrity, ensuring that data and software remain unaltered. Repudiation. Repudiation is when attackers perform actions that cannot be traced back to them. This threat can target systems like encryption keys or cryptographic logs. If attackers can alter or delete logs, they could cover their tracks, making it difficult to trace the source of an attack. The focus here is on maintaining integrity of logs to ensure accountability. Next, we have information disclosure. This threat involves unauthorized access to data, whether it's stored in the vehicle or transmitted over networks. In the automotive world, this might mean attackers gaining access to log data, personal information, or vehicle telemetry. Here, the compromised attribute is confidentiality, as it concerns protecting sensitive information from unauthorized access. A denial of service attack aims to disrupt the vehicle's operations by overwhelming a system, thus delaying or blocking access to critical services. An example would be targeting the in-vehicle network to interrupt communication between ECUs, potentially disabling essential functions like navigation or braking. This threat primarily impacts availability, which is crucial for ensuring the vehicle operates smoothly. Lastly, elevation of privilege involves attackers gaining unauthorized access to vehicle functions they shouldn't have control over. For instance, an attacker might find a way to enable or disable features like adaptive cruise control without proper authorization. This can affect both confidentiality and integrity, as it allows unauthorized changes to system settings. Before diving into the topic of visibility, 3 types outlined in ISO SC 21434 standard, which approach fits best to our TARA process. Number 1, attack potential based approach. 2, CVSS based approach. 3, attack vector based approach. As always, you can pause this video and take some time to note down the correct answer. For now, let's move on to the next slide and check the correct answer. The correct answer is number 1, attack potential based approach. Let's now discuss the concept of attack visibility ratings. This is an important metric we use during threat analysis and risk assessment to evaluate how difficult it would be for an attacker to exploit a vulnerability. The visibility rating helps us understand the level of effort an attacker would need to achieve their objective. It's crucial for prioritizing which threats to focus on. If an attack path is highly feasible, it means the risk is more urgent and needs immediate attention. Let's go over the different levels of feasibility. A high feasibility rating indicates that the attack path can be accomplished with low effort. This means that an attacker could easily exploit the vulnerability using commonly available tools or minimal resources. For example, an unprotected network port could be a high visibility target. A medium feasibility rating implies that the attack requires moderate effort. This could involve some level of skill, specialized tools, or insider knowledge. For instance, compromising a vehicle's ECU might require access to proprietary software, but is still within reach for skilled attackers. Low feasibility. When an attacker is rated as having low feasibility, it means the attacker would need to invest high effort to carry it out. This might involve bypassing robust encryption or physically accessing the vehicle's internal systems. These attacks are less likely, but still possible with sufficient motivation and resources. Finally, a very low feasibility rating suggests that the attack path can only be achieved with very light effort. These are typically the most difficult attacks, requiring extensive resources, advanced knowledge, and significant time. For example, reverse engineering proprietary hardware or firmware protected by strong security measures. Now let's do a quick knowledge check. Hopefully the ratings versus effort was understood. Let's test it out. When the attack feasibility rating is considered low, this means the attack path can be accomplished utilizing either A, very low, B, low, C, medium, or D, high effort. Once again, take some time for yourself to note down the correct answer. And if you want, you can pause this video. But for now, let's continue to check the correct answer. And the correct answer is high. So once again, when the attack feasibility rating is considered low, this means the attack path can be accomplished utilizing high effort. Feasibility analysis, which is a crucial part of the TARA process. This step is all about evaluating the feasibility of an attack, essentially how easy or difficult it would be for an attacker to exploit a particular vulnerability. In this analysis, we take an attack potential based approach, For every identified attack path, we determine an attack feasibility rating. This rating helps us prioritize our efforts by focusing on the attack paths that are easiest and most likely to be exploited. So how do we evaluate the feasibility of an attack? We look at several key factors that can influence an attacker's ability to successfully exploit a vulnerability. Elapsed time, specialist expertise, knowledge of the item or component, window of opportunity, and equipment. Let's break these factors down. Elapsed time. This refers to the time required to execute the attack. The shorter the time needed, the more feasible the attack is. Specialist expertise. Does the attacker need specialized skills or knowledge? The level of expertise required can significantly impact the feasibility. An attack requiring common skills is more feasible than one that needs advanced niche knowledge. Knowledge of the item or component. How much prior knowledge does the attacker need about the system or component being targeted? The more insider knowledge required, the less feasible the attack. Window of opportunity. This considers the availability of time to carry out the attack. For instance, certain vulnerabilities can only be exploited during specific operational windows, such as during a software update. Equipment. Finally, we assess the equipment required to perform the attack. If an attack can be executed using readily available tools, it's much more feasible than one requiring sophisticated or expensive equipment. By analyzing these factors, we can determine how feasible an attack path is and assign a feasibility rating, ranging from very low to high. This information is invaluable in helping us prioritize which threats to address first, ensuring that our cybersecurity efforts are both effective and efficient. In the next 5 slides, I will briefly go through a further breakdown of each category and examples associated with each. Feel free to pause the video so that you can thoroughly read each row. The first category is elapsed time. This refers to the time required to execute the attack. When conducting a TARA, it may help to fill this out last, as categories like knowledge, window of opportunity, and expertise play a role in how long it ultimately takes to successfully accomplish the attack. It's also important to note that not every organization may want to stick with this breakdown of levels, which is completely acceptable. You may want to further break down timelines to consider more timeframes. Does the attacker need specialized skills or knowledge? The standard breaks this down into 4 expertise types, starting from layman to requiring multiple experts to accomplish the attack. It's important to make the distinction between each so that there is awareness of how experienced the attacker must be. How much prior knowledge does the attacker need about the system or component being targeted? This table categorizes information into 4 levels, from public information to strictly confidential information, each representing a different level of access control. At the K0 level, we have public information. Next, at K1, we have restricted information. Moving up to K2, we reach confidential information. Finally, at the highest level, K3, we have strictly confidential information. This is the most sensitive type of information, often accessible only to a select few individuals under very tight access controls. An example would be a secret root signing key. This level of knowledge required for an attack plays a key role in feasibility analysis. By categorizing information according to its accessibility, we can better assess the likelihood of a successful attack. The more restricted the information, the less feasible the attack becomes, as it requires resources and access that aren't available to the average attacker. This considers the availability of time to carry out the attack. This also considers the attack vector, so if the attack is on wireless technologies that can be accessed remotely, then it affects the opportunity for access to the system. You will also want to consider how much physical access is required. There may be situations where vehicle parts need to be taken apart, which again makes it difficult to accomplish as this takes time and the opportunity to do so is limited. The last category we will dive into is equipment. We need to assess the equipment required to perform the attack. We categorize equipment needs into 4 distinct levels, ranging from standard tools that are readily available to highly specialized bespoke equipment, which are very sophisticated software tools or equipment tailored specifically for unique attack scenarios. The complexity and cost associated with acquiring and using these tools make this level of attack the least feasible. Please do take a moment to go back and review each slide and the examples associated with each breakdown. So now we have selected the associated levels. Here is an example of how we would calculate the attack feasibility level, or AFL. Each level has an associated value and rating. This rating will then be used to determine risk level later on. Before we move on, I want to mention that you might be thinking, are these not a subjective analysis? Well, yes. The selection of these categories is subjective, but this is also the reason as to why it is important to have cross-collaboration between teams to gain input. Mostly all item owners or subject matter experts on the component will know the ins and outs of the component or system and will provide guidance on what would be required to gain access to their system, which goes to show that TARA is also a collaborative effort, just like conducting a HARA. Here's another example, but also including a few other aspects we covered of the TARA, like impact and feasibility. The threat description is data flow can signal is potentially interrupted. The stride element is denial of service. The impact is high, visibility moderate, risk moderate. Under security goals we have prevent denial of service and prevent unauthorized remote access and control of the vehicle and vehicle systems. The next slides will be those references I mentioned in the beginning of this video that should help you with thinking about attack types and techniques. The MITRE framework is a comprehensive matrix that categorizes the objectives and techniques attackers use to compromise systems. Originally developed for enterprise networks, it includes 14 tactics and over 218 techniques that detail adversary behavior. This framework allows organizations to understand how attackers operate, making it a powerful tool for enhancing defensive strategies. The main question is, do we have enough visibility into adversary behavior to detect and stop attacks? The data-driven insights from MITRE can help you evaluate your current defenses and guide future cybersecurity investments. Now you might be wondering, how does the MITRE framework apply to the automotive industry? Vehicles have unique systems and challenges that require a tailored approach. The traditional enterprise and mobile frameworks don't always fit automotive environments directly, which is why the ATM has been developed. The Automotive Threat Matrix was developed to address these specific challenges in the automotive sector. Unlike the general MITRE framework, ATM is designed based on real-world automotive attacks and validated research. It currently includes 13 adversarial tactics and around 80 techniques. This matrix is continuously updated to reflect emerging threats, making it a living document that evolves with the landscape of automotive cybersecurity. For example, new types of attacks targeting vehicle communication protocols or telematics systems are regularly added to the matrix. Let's go for an example. Imagine a scenario where an attacker exploits a vehicle's telematics system to gain remote control. By leveraging the ATM framework, we can identify the specific tactics and techniques used, map out attack paths that the attacker might take, apply countermeasures based on known defenses within the ATM framework. This approach ensures that our risk assessments are data-driven and aligned with real-world attack methods. With ATM completed, its techniques and attacks defined, and threat intelligence starting to flow into it, we can start thinking some more about how this can be used for TARA modeling to support our 155 type approval. There are good opportunities to use ATM to fulfill the threat and risk assessment activities defined in Claim 15 of ISO SCE 21434. ISO SCE 21434 does not specify how to identify threats or attack paths or list any specific threats that need to be considered. So these references act as guidance and also just make it easier to have a source for information for engineers. Since ATM includes techniques that are observed to have been used, it helps make sure we don't leave out something important. The ATM should help security engineers, and especially less experienced security people, to consider a broader set of threats that they otherwise would have. And as the ATM matures, threat intelligence can feed directly into it, updating techniques, tactics, heat maps, etc. as they become available. This could help it become a faithful snapshot of threats we must worry about. In addition to referencing frameworks like ATM or MITRE, it is equally important to create internal catalogs within your organization. There are references like this from Automotive Security Research Group that shows an example of a catalog. However, building your own catalog is essential to building a repository of threats your organization is concerned about. Block Harbor has its own threat library that has been built over time. The benefit of this is to understand common threats to components and items. Up until now, we have talked about damage scenarios, threat scenarios, which include our stride, threats, and attack paths. We must know the difference between each. So to quickly recap, an attack path is a series of steps to achieve a successful attack threat scenario. A threat scenario focuses on how a malicious actor might compromise a system, while a damage scenario zeroes in on the potential consequences of that compromise. For example, a threat scenario might involve an attacker hacking into a vehicle's headlamp system. The damage scenario, however, would describe the resulting collision risk due to loss of visibility. We will end this section with a few knowledge check questions. Is this a damage scenario, threat scenario, or an attack path? The sentence is: an attacker spoofs messages between ECU1 and ECU2. As always, take some time for yourself. Feel free to pause the video. Otherwise, let's move on and check the correct answer. The correct answer is threat scenario. Now let's move on to the next question. Once again, is this a damage scenario, threat scenario, or attack path? The sentence is: the attacker delivers the malicious code to the system by inserting a compromised USB drive with malicious software. Now let's go and check the correct answer. The correct answer is attack path. Once again, is this a damage scenario, threat scenario, or attack path? The vehicle is behaving in an unexpected way. Now let's move on and check the correct answer. The correct answer is damage scenario. Up until now, we have covered item definition, asset identification, damage scenario identification, and impact analysis, and just now threat analysis. As always, I hope this was informative, and stay tuned for our last star section called Risk Assessment, where we will cover the risk analysis.